does require you to have a Kate account. I assume most of you anywhere with your account. You don't have to go through a CS server, then go to that Georgia server, right? So you can connect from anywhere, so you don't have to have a CS account. Absolutely not. So if you don't have a CS account, you don't have to worry about it. But for lab submission, you do need to have a Kate. So you should go and create a Kate account if you don't have one. As I mentioned, if you are unable to create one, then and one more time. So I will strike the importance of start early, right? So get started right away. Do not wait till last minute. And the way I plan to do this is once lab 1 is due, I will immediately release lab 2. And once it's due, I will immediately release lab 3. So we will do just one lab after another, pretty much like this till the end of the semester. Okay? Planning to do 5 or 6 labs. Alright, so let's move on. So today we're going to talk about access paths and access methods. And you need some of this knowledge for your lab 1 actually. So the idea of access paths and access methods are, you know, if you think about what we have learned so far, we learned the language model, which is essentially the application layer of a database management system. What you will see, right? The connect to the database, they interact with the database system through SQL like interface, right? Then we also understand by now the storage engine of a database system. We know that you have catalog tables that store your schema definition, attribute type, attribute values, and so on and so forth. That's the first thing you need to have. And then you have the secondary storage media, and you manage. For a database system point of view, memory is represented by a collection of buffer frames. Each frame is of page size that holds a page that has been requested by some process in the DBMS, and they will load page from disk and do page replacement if necessary. And then at the disk layer, we have the disk-based manager, which is in charge of allocating pages to different files. We know file is implemented by file structure, which is an unordered collection of pages and records, and we know how we should organize those records, depending on whether fixed length or variable length. Then finally, within each record, we know what goes into it. Again, depending on whether it's variable length or fixed length. Okay, so we kind of have those things in place. The gap, though, if you think about it, is what happens between user submits an SQL query and how that query translates to something that's executable by the DBMS and go all the way to the buffer and the storage engine and go get the data. Does that make sense? And I'm not going to talk about how to fill that gap for now, because that will be the discussion we will be having on query evaluation and query optimizer. What I will talk about today, though, is suppose you have a query plan that passed to you by the query optimizer and query executor. How do we execute the query according to that query plan? And if in the highest level abstraction we can think of is how do we go fetch a record and how do we go and write the record? And where record is represented by a record ID, RID. And what is RID? We talked about it last lecture. RID is simply a pair that has page ID value and the slot array index. That gives you a unique kind of pointer to where the record locates at. Okay? The higher level abstraction, what we're really trying to do is fetch a record. And if you extend that discussion a little bit, then you are looking at how to fetch a range of records and how to write a range of records. By a range, here I refer to a meaningful range with respect to some search condition. For example, give me all the records, student records, with GPA value between 3 and 3.5. That's a range of records you need to fetch. Does that make sense? And this part, which is how do you go about getting one particular record or go about getting a range? This is what we mean by access paths and access methods. Okay? So that's the discussion we're going to be having today. First of all, let me set up the model. So we talked about the RAND model. The random access model. But we know database systems are not using the RAND model because database system uses a memory hierarchy. So RAND model doesn't really fit what we're doing. So in a we have to design a model that captures this memory hierarchy characteristics that go into a DBMS. And this is the reason we introduced this model called external memory model. Okay, and in this model, we have 3 players. In the bottom is your RAM model right there, memory and processor. That's the RAM model. Okay. On top is that secondary storage medium. In our case, hard drive, but it could be a SSD or something else that's non-volatile. Essentially, we need to have another layer here, another player here that represents your non-volatile storage medium, which form a memory hierarchy. Okay? Some of the notation we will be using in our discussion, we use N to denote the number of items in the problem instance. In our case, N is the you can think about that represents the number of items in our record. And B is number of items per disk block, in other words, number of records that go into a disk block. N is number of items fit in memory, in the memory. Note that we, from a theoretical standpoint of view, we do not model memory size in terms of bytes. Okay? Because bytes is a relative concept. Why I say that? Right? If you go to store some characters, gigabytes is a lot, if you think about it. Right? 1 gigabyte is a lot. But if you go to store some images, 1 gigabyte is nothing, it's small. So how big your memory is really a relative concept to your application, which is to the size of your item. That makes sense? So for the same reason, we use B, number of items, to quantify how big is your page to represent page size, how big your page is, because that's really a relative concept. If you go to store, again, a number of characters, a 4 kilobytes page is huge. Right? Because that gives you 4,000 items already, 4 kilobytes, right? But if you go to store an image, then 4 kilobytes page is not so big. Maybe you can store only 1 image, and that's a small resolution image as well. If you want to store a high resolution image, even 1 page cannot store 1 item. It may not be enough to store 1 item. Okay? That's why we use number of items going to a page and number of items go to a memory to quantify the page size and memory size. That makes sense? Rather than using absolute byte values. Okay? T is number of items in your output. Okay? And I/O stands for moving block between memory, and this can be a read operation, a write operation. It's bidirectional. And of course, we assume for convenience M greater than B squared. You may wonder why we have this assumption here. This has to do with a lot of algorithms we will be discussing later on in query evaluation. A lot of algorithms, in order for them to be I/O efficient meaning they minimize the number of I/O operations between memory and disk. For some reason, this condition will arise in multiple occasions. You need to have this condition in order for a lot of algorithms to be I/O efficient. That's why we simply assume, unless otherwise specified, M is greater than B squared. M is greater than B squared, which is not an unreasonable assumption, right? If you think about it, right? If each page can hold 100 items, and each page is 4 kilobytes, B squared is what? Is 10,000. 10,000 and 4 kilobytes, that's like 40 megabytes. So that's what, 12 gigabytes already. 40 megabytes is nothing. So this assumption is totally reasonable in today's architecture. Okay? You follow me? All right. Now let's look at some fundamental bounds. Okay, once that's being set up. By internal, I mean the RAM model. Okay, by internal, I mean the RAM model. What's the cost of doing scanning operation in internal memory in RAM? Meaning scan all records. It's simply n, but note that here, this n doesn't represent n IOs. It represents n memory access, n operations. It's not equivalent to n IOs. You have to pay attention to that. Because in the internal memory sense, there's no concept of IO to begin with. You quantify the cost of your algorithm by the number of operations you have to perform. In other words, number of memory access you have to do. Then for scanning n records, you have to look at n memory locations. That comes to that value n over there. Any questions so far? What about in external memory? What about in the RAM model? Well, keep in mind, in external memory, this cost is no longer n IOs. It's not n IOs. Why? Because the smallest unit you operate over is what? Is by page or by block. You follow me? So you do not rate items one by one. Rather, you rate items by page. So with n items in total and b items per page, how many pages you need to rate in total? N over b. Of course, to be precise, should be the ceiling of this. You follow me? Okay? So that's a huge distinction right there. Okay, you have to understand what this n and what this n over b means. Okay, they mean different things. In RAM model, n means n memory access. In external memory, n over b means n over b IOs, or n over b pages or blocks you have to read. Do you follow me? Okay. Now, sorting in memory is what? We all know is n log n. That's a fundamental bound, right? Of course, we're assuming here, again, there is some implicit assumption I'm playing here, which is you are not using a parallel architecture to do this sorting. If you do a parallel sorting, you can do this in log square n round. Okay. And here I assume it's a sequential algorithm, sequential sorting algorithm. So it's n log n. In external memory, if you do n log n, of course you can still do n log n. You can carry this bound over by simply running your internal memory algorithm over the external memory dataset. But then n log n is a lot of IOs. Rather, in external memory, we are able to do just this many IOs. N over b to the log of n over b, n over b. If you wonder how I come to this bound, I will actually explain this in either next lecture or the lecture after that. Okay? There is a classic external sorting. Okay, you have a sequence I where the size is n, okay, n items. And you want to define a function called p, which give you another output I prime, where the size, the requirement is size of I equal to size of I item. And in the set, if you view I as a set, it should be the same as I prime. Because note that in set, we do not care about the order of the elements. These two sets are equivalent if you consider them as set. I'm not claiming order set. Do you follow me? So what I'm saying is the output and input contain the same set of elements. But that's not enough. Promoting sets where I prime is from belong to the set, the following set. I prime is one of the sequences from a set of sequences, where each is where each I and each II from this set satisfy this requirement. How many of them you have? Can someone tell me? What's the value, in other words, what's the value of x? What's the value of x here? How many possible permutation sequences you may have? That's the question I'm asking. Huh? N factorial. Why? For the first position, you have n choice. You choose any one of them. For the second position, how many choices you have? Minus 1. You cannot choose the same item one more time. Otherwise, if you do that, this condition will not hold. They are no longer the same set. So you have n minus 1 choice left. 2, right? So n factorial. Okay? And now that, as you know, once I define all of this, a random permutation basically says probability of this equal to any j, where j is from 1 to x. Probability this function output a sequence ij for any sequence from this set is what? Is what? Must be uniform, so it's 1 over n factorial. Okay? So that's how we define permutation. Okay? But the question here is not to define permutation. That's a fundamental concept you guys should know as a computer science student, by the way. The question here at the stake is how you generate a permutation. You may wonder why you want to do a permutation. Well, who cares about permutation? Well, this has many applications, right? Let's say I want you guys to vote for something, but you may be worrying about, oh, if you vote first, you may influence the decision made by others. For example, you cannot ask, let's ask all the Democrats vote first, then Republican. If you think about that model, that's actually a pretty bad model. Because you have a lot of independent thinkers, right? They look at the vote results. The first day is all the Democrat vote. Oh, Hillary got 30% vote and Donald Trump has 0% vote. It's like a landsliding winning situation for Hillary, so all the independent guys will vote for Hillary. Or they just give up. But actually, if you ask them to vote in random orders, that might not be the case. You follow me? It's probably 30% versus 31% within the margin of error, right? So you want to make sure people vote in any random order, not in any particular meaningful order. And for that, you need permutation to be absolutely fair, right? So that's just one example of it. There are numerous applications of this, right? So how do you generate a permutation? Well, internal memory takes n time, okay? External memory is a little bit tricky, okay? Searching in internal memory, searching for a particular record takes log n time, assuming your input sequence is sorted already. Assuming your input sequence is sorted. In other words, they organize. Then what you're doing essentially kind of like a binary tree type of thing. Okay. In external memory, this becomes, of course, you still can do log to n IOs, but we want to do much better. So you can do log bn. Replace that factor 2 with the factor b. And this actually is a huge improvement, right? Why? If you look at this, what is the difference? What's the difference of this? Right? Okay. Log xy essentially equals to log 2 of y to log 2 of x. Actually, you can replace 2 with any constant c, right? Any constant c. So this cancels out. So that's the result, right? Log 2b. and what's log to B? Suppose B is roughly 100. You can have 100 items per page, which is typically in a database setting. What's log to B? It is 8 point something. Right? Because 2 to the power 8 is 64, 2 to the power 9 is 128, so it must be 2 point something. Less than 3, bigger than 2. 8 point something, that's almost 10. Meaning there is an order of magnitude difference here. Huge. Okay? Translate to layman language, that means I give you $1,000 versus I give you $10,000. Which one you prefer? Okay, choice is clicked. Right? If I tell you I give you $1,000 versus I give you $1,200, doesn't matter. I go, you might appear to be noble.
Matters to me.
Well, matter to you? Well, but if I ask you to do something really kind of not so noble, then you may say, oh, I will definitely do, I'm not going to lose my soul for $200. Okay? You appear to be a noble man, right? So let's do the price again. $1,000 versus $10,000. Forget it, I'll take $10,000. Tell me what you want me to do. Does that make sense? Many people refuse to admit this, but I think that's what happened to most people. I would really admire people who can really say no when the price tag is there is huge difference. I wish we had politicians like that, but I think we don't. So that being said, let's do some warm up. Okay, we're gonna talk about sophisticated operation down the road, but let's do some simple warm up. Kind of like when you run for a 100-meter sprint, you don't go and run, you kind of do some stuff before you run that 100-meter sprint, right? Let's do some warm-up. So basic structure is queues and stacks. You all know what's a queue, what is a stack, right? I assume. First in, first out, first in, last out. In internal memory, that's easy, right? When you insert a queue, place to the head. When you take out item from a queue, you take from the tail. Very simple. So the cost of insertion and of to be precise, push and pop, right? The cost for internal memory is just one operation for each one of them. Okay? You of course can do the same thing for external memory. We translate to one, but here is one operation, or one memory access. One memory access to one item. That's what I mean by internal memory, right? In external memory, you can of course use the same algorithm to get one, but now it's one IO for each of these operations, right? You insert and you push, you pop. But can you do better? That's my question. Keep in mind, when you insert one item using this simple algorithm, what happens? You go to the disk, you fetch the page that this item should go to, the first page of the queue. Right? Of the tail, depending on how you look at it. Let's say we insert at end, pop at the head. Then we look at the last page of the file, there's the heap file for your queue. You go grab the last page, fetch that page to the main memory, insert the item, and write it back. So it's actually two IOs, right? But if we use big O notation, 2 and 1 are the same. Okay? 2 and 1 are the same. Actually, if you talk to, this is what I always make fun of my dissertation computer scientists. They always use big O notation to hide constant factors. If it's 1 or 2 different, that's okay, but sometimes the constant can be as big as a billion. And they still claim billion is still a constant. We don't count it. Okay? Because it's not a variable, right? Variable can change because if it's variable, you don't know how big this value can become. But the point is, for a lot of problems, the possible range for that variable is way less than the billion. And you hide that billion factor, sometimes it's 10 to the power 9x. And once you use big O notation, this becomes X. But X is probably in the range of 1 to -10^6. That's where I find it's kind of funny, right? But a lot of serialization use this trick. Here, I'm not playing tricks. It's word 1 versus 2, so I can actually use big O notation, right? So no problem. Okay, do you follow me? But can you do better? Seems like you cannot do better, right? You have to pay this I/O to insert one item and delete one item. Okay, when you do deletion, you fetch the head of the heap file page to the buffer, delete the item, write it back, 2 I/Os for one item operation. Can you do better? Well, depending on how you do this, right? If you do this per item, then nothing you can do. That's what you have to do. Okay? But if you do this for every B items, you can improve this to 1/B. This back in there for both insertion and deletion. The idea is as follows. I'm going to show you this small animation, then you should be able to understand what's going on. Keep in mind, this represents not one item, but represent one page of data. One page of data. Okay? The box over there represents one page of data rather than one item. And what happens? Okay? That's the pop operation. You understand what's going on? Yes or not? No? I see some puzzle faces. Okay. You raise a page into buffer, which is this last page over there. And then you pin this page in the buffer, meaning you set the pin count equal to 1, you never decrement that pin count, meaning you cannot replace this buffer frame. You pin that page. That's what I mean by pin the page. And then any follow-up pop operation can be served without incurring any I/O, because that page is already brought into memory. You don't have to keep going back to disk and get a page. It's already in the buffer. That's what I mean by pin it. That's the reason why people call it pin count. You want to pin something on the wall, right? Right? You do this, right? I do this all the time. You pin it on the wall. If it's important, make it stay over there. So you keep popping item from there. And when you have eliminated all items from that page, what do? Now you do have to pay an I/O cost, which is go back to disk and delete that page from your file, and also pin the next page, which is the second page from the tail, because you need to be ready to keep popping items from it. So that's when you do an I/O. What about push? Well, same thing. You allocate a new page in the buffer, and you keep inserting item into that page, but you do not write the page back to disk whenever a new item is inserted. Rather, you wait till the page is full, then you push back to disk, then you do this again. So how many I/O you do? Well, every B items you do 1 I/O, because that's the size of your page. So the cost is 1/B instead of 1. So you wonder, wait a minute, who cares? 1 I/O is small enough. Why you bother to do this 1/B? Again, B is, keep in mind, B is in the order of 100. Right? So 1 random I/O is roughly, in today's architecture, is roughly milliseconds. Let's say 1 millisecond for 1 random I/O. Which means if you are Amazon.com, you can do 1,000 queries per minute. Right? 1 I/O, 1 millisecond. If you do this, you can do 1,000 operations per minute. You follow me? Let's say I'm going to make $1 profit per second. 1,000 operations per second. Let's assume I'm going to make $1 profit from each new customer, inserting customer, and from each customer leaving the queue or entering the queue. That means $1,000 profit for Amazon per second. Okay? That they can make money for. Now, if we use this improved algorithm 1/B, B is, let's say, 100. What's the picture? Well, how many operations can do per second now? 100,000 operations you can do per second. Again, $1 profit per operation, that's $100,000 versus $1,000. You ask me whether Amazon.com care about this or not. They don't care about how fast you can do it, but they care about the profit they can make. And because of that, they will fire you and replace whoever knows how to do this right. Does that make sense? Okay. Now, same thing goes for stack. Now you know how to, if you know how to do this for Q, you know how to do this for stack. Again, it's 1 over B rather than 1. Okay. So that's kind of our warm-up exercise, right? So now we know there's a huge difference between internal and external. This external can be a hard drive, can be an SSD, can be whatever your secondary storage media is. So even knowing this, you should be careful in writing your code nowadays, right? For example, whenever you write data to a file, do not write record by record. You always do buffer byte and buffer bit. The reason is precisely this. If you don't trust me, you can do a simple experiment using Java or C++ or Python, whatever language you have. In one code, you write 1 million records one by one to disk. In the other experiment, you write 1 million records page by page to disk. I bet, I'm willing to bet my money on it, you will see 10 times different at least in terms of the cost of your program. Okay. Now, for this reason, probably you don't know why there's a huge difference before. Now you should know why there is a huge difference. Because you're doing 1 million IOs versus 1 million divided by page size number of IOs. Huge, huge difference. Now, so that's the basics. Now let's talk about some more involved operations. Recall we talked about heap file, right? We talked about heap file. And the operations we need to support from an abstract point of view, coming down from the query evaluators. What the query evaluator will tell you is, go get this record for me, go get a range of record for me. I'll write this record too for me, I'll write this range of records for me. So that's kind of the abstract view from the heap file. Imagine you are a heap file, right? You're looking up, you're waiting for instructions coming down from the evaluator. The query evaluator and query optimizer are in charge of coming out with a reasonable query plan. But from the eye of the heap file, I don't care about the query plan. All I care is tell me what record to fetch for you. I do this first, then I do that operation next. The order of different operations, that's the job of the query planner and query evaluator. I don't have to really worry about that. From my point of view, I only care about, okay, go get this record, go do that. So this is kind of like the abstract view in terms of operations that heap file needs to support. So we'll look at how we're going to do all of these operations. Okay? And in particular, we're going to look at a few different alternatives. We all know what is a heap file, right? Heap file is an ordered collection of data pages. That's it. But we also have, in contrast to heap file, we also have sorted file. A sorted file is a true heap file. True heap file means it's sorted. Because heap, in internal memory data structure, a heap is sorted. Right? But in external memory, heap file refers to unordered files. Right? So in contrast to heap file, we have sorted files. Sorted file sort is data pages by the search key. Keep in mind, a search key has nothing to do with the concept of key for a relational schema. A search key is simply a collection of attributes that you sort your records based on. Okay? For example, if your data pages in a heap file is sorted by first name, then last name, then the search key is a combination of first name, then last name. So search key can be a composite set of attributes rather than just a single attribute. When I say it's sorted by first name and last name, what that means is you sort by first name first, you break tie if there's a tie on first name value by looking at the order of the last name. Okay? And then we also have cluster file and uncluster file. I will talk about those later on, but let's focus on heap file and sorted file first. And here is our assumptions. We ignore CPU cost because when you do these I/O operations, I/O cost dominate over the CPU cost. So we ignore CPU cost in this analysis because we are doing simple operations: scan record, go write a record, go read record. We are not doing expensive computation CPU-wise, right? It's not like we fetch those records, then we do a TSP, traveling salesman problem over those records, then come back and write those records back to disk. That CPU cost might be expensive, but we are not doing that. We are simply doing scanning, read and write, simple operations. So CPU cost is very minimal compared to the I/O cost. So we ignore CPU cost. And N over B, if you think about it, is the total number of data pages in your file. Because you have N items in total and B item per page. So N over B is the total number of pages you have for your file. Does that make sense? And D is assuming we have some measurement on average time to read and write a disk block. Of course, this is a very rough estimation because when you try to measure the time taken to read and write a block or a page, you really have to be specific about whether this is a sequential I/O versus this is a random I/O. There's a huge difference there, right? But for our discussion, we simplify this. We simply say, okay, we use D to quantify, to represent the time taken to read or write a particular page. By the way, a page or a block refer to the same thing, a page or a block of data. And for the most part, we do average case analysis, but when applies, I will also tell you the best case and worst case analysis. Okay. And some more assumptions in the analysis. We assume we are doing single record insertion and deletion, unless otherwise specified. And for equality search, when I'm trying to do an equality search, for example, give me the student record with student ID equal to 1, 2, 3, 4. That always match to just one record, right? But if you do a search on student name, for example, give me all students record whose first name equal to Mike, and you may end up with hundreds of Mikes, hundreds of records, right? And this is a variable. If you change the name to John, you may have, I don't know, 200 or less. So it could be a variable. But here, for simplicity, we assume that for equality search, unless otherwise specified, we'll always assume there's only one matching record to simplify our analysis. But in reality, this could be a variable value rather than a constant, just one. Okay. And for if a file is sorted, we consider two alternatives. One is you do this packing operation. The other one, you do not do the packing operation. By packing, what I mean is you leave no free space, not only in just a single page, but across different pages. You do not leave any free space. Okay? So that will become clear in a minute once we start doing this analysis. Okay? The objective is to fill in this table right here. Okay? So for heap files, what's the cost if you want to scan all records? What is the cost if you want to scan all records? I/O cost, number of page operations you need to do. Well, which we have done already, right? Essentially, the first bump over there. If it's in internal memory, scanning all records translates to N memory operations, but in external memory, this translates to N over B page access, right? Because those N items will sit in N over B pages. So this is simply N over B. And if you want to, but N over B is the number of I/Os you do. If you want to quantify the time, this becomes N over B times B. Of course, that B, the value here, should represent the time that costs for one sequential I/O. Not because you are doing sequential I/O here. You're reading them one by one in sequential order. You are not doing random I/O. So you have to be careful in what is that value D represents. It represents sequential I/Os. For the subsequent analysis, I will drop that term D. I will focus on the I/O analysis. But whenever it applies, I will tell you whether it's sequential I/O or it's random I/O, because the two have a huge difference. What about equality search? What's the value for a heap file? Can someone tell me? You're trying to find a record. Let's say, give me the student record with student ID equal to 1, 2, 3, 4. What is the cost? If you try to do this over a heap file organization. If you try to do this over a heap file. How do you find the record with student ID 1, 2, 3, 4? In other words, I'm doing this query. Then I'm doing this query right here. What is the cost? If I do this over, let's say student is stored in a heap file, right? That's essentially what I'm doing here. What is this cost? What's the best case? What's the worst case? And what's the average case? Okay, I will do this, then I will ask someone to do the sorted file analysis for me, okay? The best case, because it's a heap file, it's not sorted in any order, right? To find one particular record, you have no choice but going over all records until you find the record you want. You follow me? So what's the best case? Best case, you're lucky. The very first page you read contains record 1, 2, 3, 4. You read, you're done. So best case is just one IO. What's the worst case? Well, it's the last. Actually, this happened to me last semester. A student came to my office trying to get his or her homework. And I have a pile of homework, 130 copies. And I remember he started searching for his name. You know what? It so happened he is really the last one. Yes. Okay? So that's the worst case. But over there, if you think about what he's doing, he's using an internal memory algorithm. He's looking at one by one. He's not looking at block by block. Does that make sense? Block by block means you look every 20 homeworks at once. He's looking at one by one, so it's so that's why the cost is actually n, right? Where n is 130 in that particular case. But in external memory, we count IOs. You still have to look at every record, but you only pay one IO every B record. Because for every B of them, you bring them to main memory, you scan through them in main memory. That cost is very small compared to the IO operation. So we do not count that. We only count IO operations. So the worst case is N over B. What's the average case? Assuming a totally random distribution, roughly you spend half IOs of the worst case. So the average case is half of N over B. Okay? That said, let me change my condition a little bit. Here you assume that you know there is only one matching record. Suppose I change this query to first name equal to Mike. Okay, what's the cost of this query when you do this over a heap file? What's the best case? What's the worst case? What's the average case?
So you have to go over all of them no matter what.
You have to go over all of them no matter what. Excellent. Why? Can you explain?
Because the first one and the last one could both have the first name.
Yeah, because the first one and last one, until you have seen all records, you don't know whether you have found all marks or not. So you have to go over all records regardless. So that's the best case, worst case, and average case. It's always N over B. So what's the difference? The difference is when you do this query, right? You know that student ID is the primary key. So you know there will be only one matching record. So as soon as you find a record, you can stop. You can safely stop. Does that make sense?
Is that what index is?
Index is for different things. I will talk about that in a minute. Okay? Okay, so that's this cost. What about you call the search over a sorted file? Or a sorted file. The naive solution will be, of course, we assume we have the assumption that the equality search is over the search key attribute. Meaning the file is sorted by first name or is sorted by student ID when you do these two searches respectively. Because otherwise, if you're doing a sort on first name and the file is sorted by student ID, effectively to you it's just a heap file. It's not a sorted file. Does that make sense? So we assume you're doing equality search over the search key that the file is sorted over. Okay? And what's the naive approach? Well, naive approach is to ignore the I/O model completely. I just do binary search, which is log2n, which means I find the middle record, the record in the middle, and I can figure out which page contains that record, right? It's roughly that page contains that record. And use that record compared against my search condition. If my search condition is greater than the value of the search key on that record, what I do? I go to the otherwise I go to the either go here or go here, right? Then I recurse. After log2n operation in the worst case, by the way, log2n here is the worst case, I will be able to find my record in the worst case. Typically, you might be able to stop earlier than that. If you're lucky, 1 IO. The best case is 1 IO, worst case is log2n. Average case really depends on the distribution of the values and what value you're searching for. Do you follow me? The question is, can you do better? The question is, can you do better than log2n? The answer is yes. And it's not that difficult to come up with a better answer. You do the same thing, but you do binary search over pages rather than binary search over records. Everything stays the same. But you do binary search over the pages you have, because pages are sorted. Okay? Rather than simply doing binary search over your records. Then what do you end up with? Well, instead of doing this many IOs, you end up with this many IOs in the worst case. Okay? Of course, the best case is just 1. Okay? What about range search? I'm searching for, oh, by the way, before I proceed, let me ask the same question. So this is the cost for doing like this, right? What is the cost for doing a query like that? First name equals to mine over our sorted file. Suppose the file is sorted over the first name attribute. In other words, the search key of your file is first name. What is the cost? What is the query cost? Well, obviously, you still need to pay this cost. What does it give you? That gives you the page and location on that page of the very first record with first name equal to Mike. If you go to the left, even just by one record of that record, you will find a name who, otherwise ranks smaller than Mike. For example, maybe Meg. I don't know. It's ranked before Mike. Right? Some names are ranked before Mike. Okay? And if you go to the right, what happens? Or it could be a record with name with rank order larger than, greater than Mike. So for example, give me a name. I just made up a word, okay? Then the end is fine. But you never know. People have, different names. Right? Different names. When I first came to US, that's kind of interesting. I went to BMWay in Massachusetts, and they look at my name. Wow, that's a weird name. That's the first word I got. I was like, no, my name is not weird.
You said, no, your name is weird.
No, but that's fine. It's it's fine. I understand. But that's essentially, that's why I don't want to say this is a weird name. I just say that's just another name. Okay. But I do have an open mind. I'll keep that in mind always. Okay. People can do whatever they want. That's their choice. Okay? As long as it doesn't object what other people are doing. If you interfere with other people are doing, then you have to be careful with your choice and actions. Okay? Now, that name, if you go to write, this is what you may say, right? But you may also say another Mike, whose last name is different. Or it could be that even the last name is the same as the preceding record. Two students can have identical names, just differ by student ID values. You follow me? So how do you do equality search? Well, you go all the way until you find first such record where the first name is not equal to Mike. And you can do this by paying a number of sequential IOs. Keep in mind, you still do page level access. You read one page of data at a time. You don't read record by record, you read page by page until you find the first page that contains a record with first name not equal to Mike. Then you can stop. And you can for sure you can rest sure that you have found all the Mikes because they are sorted. Whereas in the heap file case, you can't do that. You have to go all the way to the very end, to the last record. Does that make sense? Okay, so that's the difference between the two. Okay. And in this table, I assume there's only one matching record. Otherwise, this number here, you have to change this number with how many additional IOs you have to do. And how many additional IOs depends on what, by the way? If we use T to model the number of items for a query output, remember T is obviously a variable, right? For different queries, the value of T is different. But if we do use that to model the number of items in the output, the number of additional pages you have to read is simply T over B. Because each page has B items, you have T items in the output, that translates to T over B IOs. And these are, by the way, these log 2 N over B IOs are random IOs, but that T over B IOs are sequential IOs. So it could be the case that T over B value is bigger than the log 2 N over B value you get, but the actual query time of the second component is way smaller than the first one. To be precise, you have to have this condition. Sorry. Yes. You have to have this condition in order for the first part to be more expensive than the second part. Why? Because, as I said, typically in today's architecture, sequential I/O is an order of magnitude less expensive than random I/Os. That's why you have this relationship over there. Okay?
Question.
Yeah.
What if it's, in this case, we talk about the record in unique, right? What if it's not unique and two records on two different pages?
Well, that's essentially the T over B term try to quantify.
Okay.
They will span in the worst case. Well, of course, it's a sample issue. I think what you're saying is, if T equal to 2, okay, and T over B, of course, is less than 1, does that mean you only pay 1 IO for this? Well, not necessary. Those are the boundary cases that we cannot capture precisely using a generic formula. Because it could be that the first record with Mike is here, and that next record with Mike is just over there. They just happen to span over 2 pages. So even though T over B, if B equals 100, T equal to 2, is less than 1, it doesn't necessarily mean you pay just 1 IO. So to be precise, in the worst case, you pay this many IO. T over B, the ceiling of that guaranteed to work. In the worst case, you pay no more IO than that, plus 1, of course, to counter for the boundary case. But most likely it will be something like this. If you have 2 Mike, you have to be really unlucky that one is here and the other one is here. In most cases, it will be like this. And by the way, if that's the case, this page is already accounted for by that log 2 n over b term. By the time you finish that binary search, this page is already accounted for. So you don't have to actually add another IO to it because it's already in the binary. That's why I think, to be precise, you just take the ceiling of this without plot line. That will be okay. Because the first page in your output range is already counted for in the log 2 n over b term. Okay? But those are really boundary cases, you can be a little bit hand-waving over them, as long as you've got the big picture here. Okay? Now, what about range search? Range search meaning, give me a student record with student ID, okay, you just write it out. Okay? Range search is occur like this. Select from student, where student ID greater than 100, less than 1,000. I'm looking for the hundreds to the thousands students in University of Utah. Okay, that's what I want to do. And of course, for a sorted file, we assume the file is sorted over the search key you're doing. They're sorted with respect to the SID value here. But let's look at a heap file first. What happens for a heap file for range search? Do you know what's the cost for this? You have to go over all of them. Like in that equality search when you don't know how many matching records. The same thing happens here. If it's a range search, you don't know how many matching records you're going to have, you have to go over all of them. However, on the other hand, if you think about this particular application, assuming each student ID value is taken by a student, meaning there are no student ID value that's not used. You know exactly there are 900 students here in this range. So as soon as you see that 900 record you found, they could come in random order, by the way. The first student you found might be 888, then the last record you found might be 101. They come in random order, but you maintain a count as how many you have found so far. As long as you have found 900 students, you can stop. But you don't know. But even that being said, you don't know when that will happen. It could be you're lucky all of them are in the first 10 pages, or they span over all different pages. You have to go over everything. But in the general case, let's say, such as UCK, you simply don't know how many students are in that JPA range. And in that case, you're hopeless, right? You have to go all the way to the end. Because unless you have seen all records, you cannot be sure you have found all you are looking for. Okay? So the cost here for heap file for range search is best case, worst case, average case is all N over B. What about binary search? Well, it's similar to the discussion I just had for equality search, but with multiple matching records. For binary search, you use for sorted file, you use binary search to do a search on that smallest value in your range. That gives you the page ID and location of the record on that page for the very first record that possibly fall within your range. And because it's sorted, then you can do linear scan afterwards for T over B IOs to find all matching records. So that's essentially the cost. Okay?
That's for the range.
Yeah. Okay. So I'm just showing if you know the matching records, or if you don't know, or if you assume just one matching record for the equality search. For range search, that's essentially what happens. Yeah.
If there are enough records in that range, would it ever be better to do two binary searches, once to find the first one in the range and once to find the first one that's not in the, or the first one that's above that?
Well, if your goal is to retrieve all of them, do two binary search to it doesn't matter, you have to still scan all of them anyway. But if your goal is to just find out where the range starts and ends, that's obviously better than doing a binary search and doing a range search. That makes sense. But if your goal is to do reporting, then yeah. Actually, there's some cute idea over there because in in database queries and in a lot of operations, we actually differentiate what we call reporting queries versus non-reporting queries for that reason. Because reporting queries, for reporting queries, there's a fundamental bound, a lower bound. No matter what you do, even if you ask God to help you, you have to pay that T over B cost. Because that person, whoever that person is, needs to do the output. Does that make sense? For reporting queries. Does that make sense? However, for non-reporting queries, oftentimes you can do better. I'll give you an example. Let's say I want to calculate the average income for Salt Lake City population. The naive way of doing that is to treat it as a reporting query, which is from the population of Utah, I find who has a city value equal to Salt Lake. Then I go through all of them, add them up, the salary or income, add up that value. Then I do a division. I maintain a count at the same time. So I treat this as a reporting query. I find all person living in Salt Lake City, I aggregate over, then I do a division. I can report the average value. That makes sense? But if you think about it, if you allow me to do some pre-processing, I can do this much better. What I do is as follows. For each county in Utah, I maintain the average income for that county and the total population for that county. Now, if you ask me what's the average income for Salt Lake City, just define me what you mean by Salt Lake City. Okay, if you tell me Salt Lake City contains these few counties, I simply need to go to those few counties, check their average value and total population, multiply plus, then divide by the total population. That can be done much quicker than reporting or than treating this as a reporting query. And that structure you maintain, that tell you the average income for each county and total population of each county, that is what we call an index. That's one example of index. You have many, many different representations of index. An index is nothing else but a data structure that you build and maintain over your data to facilitate your query answering. And we generically call that an index. Okay? It can be many different things. Finally, what about insertion and deletion? Well, for insertion for a heap file, that's easy because you maintain no particular order. So you just go to the last page, read the page, update in the buffer, make it dirty, and write it back. So 2 IOs. You have to read and write. For a file that's stored, it's become a little bit more tricky because you cannot just insert in random location. You have to insert the new record but still hold the sorting order, still maintain the sorting order. So what you have to do is to do a search first to find the page that the record should go into, then write that record over there. That happens in the buffer, then mark that page to be dirty and write it back. So the total IO cost is simply the search cost plus 1 IO to write it back to disk. Okay? This is assuming you do not do the packing operation or unpacking operation. Packing, as I explained, you want to leave no free space within a page and between any pages. If you don't do that, you assume the page always has some free space left. That's weak. But if you want to do packing operation, you don't want to leave any free space in any given page, what happens? Well, it becomes much more expensive. You still have to do the search operation to find where that record located at. You try to delete, and you delete that record. Once you have deleted that record, you leave some hole in that page, right? So you move all the records coming after that page forward by the space occupied by that record. And this applies not only to the record that locate on the same page with the record being deleted, but happen to all the records located after the page containing the record to be deleted. And on average, how many pages you are looking at? On average, you are looking at half of the pages on average, because the deletion can happen anywhere in your file. So on average, you are looking at half of the pages. You need to do this packing operation. And for each page, to do the packing operation, what we have to do? You have to read the page, move all the records, and then write the page back. So the total I/O cost is simply 2 times. That's why you get this value right there. Okay? And insertion is similar, but one thing that's different from deletion for the heap file case is in order for you to do deletion, you have to find the record to be deleted. And that's a search operation. Assuming, again, you are deleting just a single record. And that's why you have a 0.5 N over B cost over there. That's simply the search cost. Then once you find it, keep in mind as the time, but as soon as you have found the record you try to delete, that page is already in the buffer. That's why you don't have to pay additional I/O to read that page, but you do have to pay additional I/O to write that page. So it's +1 instead of +2 for that reason. And for sorted file, if you assume you do not do this packing operation and you assume there's always some free space left on any given page, insertion and deletion is easy as well. You find the page and you delete and mark it dirty and write it back. Otherwise, you do have to do this packing operation again, which is this cost. Okay, that's the N over B term over there. Okay. All right, so we're done with the basic analysis. Now let's move on to a more sophisticated analysis. Okay, more sophisticated analysis. So the big picture is this, right? So we have this database kernel here. So we're done with these guys, buffer manager and DSpace manager. And we are currently in this layer right here. So like I said, the way we cover data kernel is bottom-up approach. You SQL query come down here. We are going bottom-up. So we are at this layer, access methods. Okay? But SQL query will come down from the top, right? Go through the parser, query optimizer, and query planner. And then finally go to your file and access message, which translate to give me this record, give me a range record, and so on and so forth. So to continue our discussion, I need to just give you a quick overview, a quick preview of what the query plan looks like and what the operator looks like. Because actually in lab 1, you need to implement a very simple query plan and a very simple operator, which is sequential scan, which is this one. You need to implement this over a heap file, N over B, essentially, and you just read page sequentially. But what's special about operator implementation inside the kernel is they have to follow this volcano model. Which I will explain in the next few slides. And then you will understand why it's called a volcano model. Why it's called volcano. Okay. So a query plan is always represented as a tree structure. To be more precise, a query plan is always represented as a DAG, directed acyclic graph. Directed acyclic graph, which basically translates to a tree structure. There are no cycle in it. Okay? So for example, if you want to do this query right there, the query plan for this will be represented as a tree to the right-hand side. So you do a heap scan over, of course, what's omitted here is the student heap file at the bottom. So what you do is you do a heap scan first, which is essentially what you will be implementing in lab 1. That will be IOs over all pages, very simple. And looking at this query, you know you don't have to keep all attributes from a given record. You only care about name and GPA. So during the heap scan process, you purge out name and GPA values. You keep only those attributes. You strip off all the other irrelevant attributes. And then you send those pairs, set of pairs, it's a set of pairs, one pair for each record you get. You send this set of pairs to another operator called sort operator, which will sort them based on name, then GPA. Why you need to do sorting? Because you have the distinct operator. I briefly talked about how we remove duplicates from a set. There are two approaches. One is hashing, the other is sorting. Once you do the sorting, you can remove duplicates by a sequential scan. So here I go with sorting. So I sort them, then I subject the output of the sorting operator to the input of the distinct operator. And then finally that's my output. Now you can see from this simple example, what happened is a query plan is simply like a pipeline process. Right? You start from the heap file, go through different operators, but each operator takes the input and produce an output that will be sent to the input of the next operator. Okay? So here is a slightly more complicated operation, because if you think about this example here, it's a single table operator. It's a single table operator. But oftentimes we have multi-table operation, like a join, right? Which can be represented by a query plan like this. This is the join between departments and employees. So you have department and employee, and you do the join, you sort, you output. Okay, that's another query plan over there. That being said, to implement any operator in this DAG structure, we follow this volcano model. In particular, we all follow this iterator interface. An iterator is an abstract class that encapsulates the following APIs. It always has an initialization method, a next method, and a close method, and an input array of iterators. Let me explain this one by one. Let's first look at this is a member variable for this class. And what it is an input array of iterators. Why it has to be defined like this? Well, if you look at from these two examples, you know why. Any given iterator, if you look at this iterator here, its input is simply the output of another iterator, right? So I can simply represent the input of this as a reference to another iterator. Whereas in this case, this iterator right there, its input composed of two other iterators. So it's simply an array of iterator interface. That's my input. You follow me? Okay. Now, once we understand this, let's understand what's initialization and next and close. Initialization is to initialize some initial state. Next, if you think about it, what happened is whenever an iterator like this one, right? What happens? If you think about this two, actually, it's easier to understand. How do you implement that distinct iterator? Well, you keep calling. How we remove duplicate using sorting? You remember? Well, we sort them, they become like this. Then you maintain a pointer or iterator over them. You keep looking at the next operator. Sorry, next element. So that's why for every iterator, there is a method called next, which basically keep asking the next element from the preceding iterator in this DAG structure. And now you understand why this is called a volcano model, because volcano, if you think about how volcano erupts, one at a time, one by one, the lava come out, right? One by one. They don't come out at once. It looks like they come out at once, right? The big volcano eruption. But if you slow down the time, right, they come out one by one, essentially. There's the pipeline, they deep down in the earth, they all come out, right, one by one. That's why it's called volcano model. Okay. I think I will stop right here and continue. I'll give you an example of the scan, and this is essentially the scan operator you need to implement in your lab one. Okay. We'll continue from here next lecture, which is Tuesday next week. Okay. All right. Thank you.